Okay, solutions to the exponential test. The first one is doing the derivative of this e to the function, and we can represent it as e to the f, where f is this function, and you can do the derivative function to get that there, and you plug it into the formula for the derivative, which is f dash e to the f. Plug those two things in and you've got the answer. The next one is a linf, because it's ln of the function, so we'll call it linf, where f is defined as that, the derivative f dash is that, and you plug it into the derivative for linf, which is f dash on f. C is a product rule, because that is u and that is v, so define those two functions and then work out u dash and v dash, and substitute it into the product rule derivative u dash v plus uv dash. D, you need to change this bottom denominator into a power -1, bringing it up the top, and then we can go into the derivative using the chain rule. The -1 comes out the front, giving -10,000. You take one off the power, and then you follow up by the derivative of the bag, the derivative of the bracket, which is sitting here. And this is f dash e to the f. This one here, y equals e to the 2 root x. First thing to do is recognize that as the function e to the f. So you could write the function over here and do the derivative. I'm going to put the -1 in to both of these powers, and 2 to the -1 is a half, and then to do the derivative, -half comes out the front, giving -1/4. Plug that back into the derivative over here, f dash e to the f, and that's the answer. This one here, I've changed f and g into this type of question, 3 to the x. It's a number to a variable, so we need to change that to a base e, because they're the only sort of derivatives we can do with a variable as the power. 3 is equal to e to the ln 3. You now use your power to a power rule, you multiply them, so that's x ln 3. And now we do the derivative of this one. So this is f dash e to the f. The derivative of x ln 3 is ln 3. Simplify this in that form. Ln of this plus ln 3. First thing to do is the number 4 comes out the front. Then you can use the ln rule with this, so that's ln 3 plus ln e to the -2x, but that's 4 times all of that, and so that's going to be 4 ln 3 plus ln 3, and we've also got the 4 in there, which is being missed out. The ln and e cancel out, and so that's really -2x, but it's 4 times that. And so it's 5 ln 3 minus 8x. This one here, have to write in the form a times 2 to the b. First of all, we bring the half up to the top, so that's 4 to the half. 4 to the half is root 4, which is 2, so that's ln 2. 1 is the same as ln e1. When we subtract lns, we can divide the powers like that. E and L cancel, so it's 2 on E, but to put it in this format, we're going to have, we can actually pull the 2 out to the right, and we've got 1 on E, that's your A value, and 2 to the power of 1, so it's 2 to the power of B, B is 1. Find the equation, the normal to that function. First of all, we need to find the contact point and also the slope. Now the contact point is at the x-intercept, so we put y 0, put 0 into there, and solve for x and get e squared, so that is the x-intercept. To find the slope function, we've got to find the derivative of this. Derivative of this one is 1 on x, and now we can work out the instantaneous slope by plugging in the x value, which is e squared, plug that into here, and so the derivative is 1 on e squared. That's the instantaneous slope at that contact point. But we want a normal, so we're going to flip that upside down and do the inverse sign, so it's minus e squared on 1. Now the equation of normal is y take y1, x take x1 equals slope. So the point we're using is e squared 0. So y take 0, x take e squared equals the slope of the normal minus e squared. And you could rearrange that, multiply that bottom over the top, over to the top line on the other side, and expand. Find the turning points and inflections of this graph. We need to find the slope first of all. That's a product rule, so that's u, that's v. Work out u dash and v dash, plug it into the product rule, and that comes down to this. The turning point occurs when the derivative is 0. That's what this is. Find the turning points and the inflections. The turning point when the derivative is 0, so we put 0 for dy dx, is here, which is down here, equals this function, equals that function. Now that equals 0 when either the first bit 0 or the second bit 0, because they're being multiplied. So either that 0, which can never happen because e to the power e to the x graph, or even minus x graph, sits entirely above the x-axis, or the other bracket 0, which means x is minus 1. So that's where the turning point occurs, at minus 1. So we can do a sign diagram to see if it's a local max or local min. So we put minus 1 on the x scale, and we substitute the numbers into the derivative. So you could try minus 2. Substitute minus 2 into the derivative, into this derivative here, and it will turn out to be a positive value. We substitute something bigger than minus 1, like 0 or 1, into there, you'll get a negative value. Because it goes plus minus, it's a maximum. In other words, the slope goes up and then it goes down, so it has to be that sort of a shape. The sign diagram proves that. So this occurred, we now need to know the coordinates of this maximum here. We know the x value is minus 1, but to find the y value we've got to plug minus 1 into the y. So if you go back and see the y function, which is up here, this one here, we need to put minus 1 into x, and that's what's happening here, and so we get e. So the local maximum is that value. Eventually we're going to graph this. We just skip down to the graph and you can see that's where the local maximum is there, 1e. Now we have to find the inflections. That's where it changes shape. Inflection occurs when the second derivative is 0. Just before I do that, the x-intercepts here, the x-intercepts is when y is 0. Put y 0 and solve that. So either that's 0 or that's 0. That can never happen, so it's when x is minus 2. So you can see the x-intercept down here is minus 2. Now we're trying to find this inflection, this point here. That comes from the second derivative being 0. So this is the first derivative from above. Now we do the derivative of that. That's a product. That's u, that's v, which is over here, u and v. So you work out u dash v dash and plug it into the formula. And then once again we've got two brackets, this one and this one. So if it's 0, either that's 0 or that's 0. That's never, but you could have x equals 0. Now to work out the y coordinate, you substitute 0 into the y, and so that's the y value, and we get 2. So we can see that's the inflection sitting there. The inflection is going from a concave section, that concave, to a convex. It's changing shape. So it's going from decreasing decreasing rate to an increasing rate. The next question is this exponential. Find the x and y intercepts. Can't do this algebraically. Y-intercept, you'd put 0 in for x, and so it's just 1. Determine where the function changes from a decreasing rate to decreasing at an increasing rate. So that's like above where we're talking about the inflection point. We need the second derivative to be 0. So here's the first derivative using the product rule. Here's the second derivative using the product rule. Now that is going to be the inflection when the second derivative is 0. So put 0 there, and we've got, once again, two factors, that times that, so either the first one 0 or the second one 0. That can never occur, and this one here is when x is 1. So it occurs when x is 1, plug it into the y value, which is this working here, and we get this value, e to the minus 2 plus 1. So that's the coordinate of the inflection. Explain the behaviour near the asymptotes. That's asymptotes when the function approaches a certain value. So as x tends to infinity, it looks like this. We've got e to the minus 2x, that would be e to the 2x, e to the minus 2x would look something like that. As x tends to infinity, this is getting closer and closer to 0. This is x here, and tending to infinity is going to the right. So as we go to the right, this is going to go to 0. E to the minus 2x will go to 0 from above. It's heading from above and getting smaller and smaller. If that's going to 0, then if we multiply by x, it's also going to go to 0, because anything times 0 is 0. So that doesn't change it. And also, if we put a plus 1, that means instead of going to 0, it's going to go to 1, because that whole curve gets shifted up by 1, which goes like that. So the asymptote will be at x equals 1. Determine the exact values where the graph intersects this. So there is the original function, there is the new function. They'll intersect when they equal each other. This is where you have to take everything to the right hand side and make it equal to 0. And you have to recognise this is one of that special case which, if by multiplying by e to the x, you'll get a quadratic. This is the quadratic. Factorised form is like that. And so either that one's 0, which means this equals that and that equals that, or this is 0, which means that equals that and that equals that. Question 5, we've got a ln function and an exponential function. We need to explain why ab squared equals ln b. Well, b lies on both lines, so we can substitute b into both of them. Substitute in the first one, you get ab squared. Substitute in the second one, you get ln b. Because it's the same point, we can say that they both have the same y values. They also have the same slope because they are touching. So we can find out the derivative of the first line, and we can get at the derivative of the second line. Now at x equals b, we'll get the instantaneous slope, which is 2ab, and substitute b in there, 1 on b. So those two have to be equal because they're at the same point, have the same slope. So that's equation 2 we've got now. So we've got two equations, one up here, 1 and 2. And that's the two equations there, equation 1, equation 2. Deduce that the point of contact is this thing here, so we have to work out the coordinate. To do this, we can just now use simultaneous equations. So we're going to substitute this into equation 2, and so that goes into there, and solving all of that, you get b equals e to the half. If you substitute that back into equation 1, back into this one up here, you'll get the a value being 1 on 2e. So the contact point therefore is bab squared, because up the top here, when x is, at that point x is b and the y is going to be ab squared, so it's bab squared. That's listed here, y equals ab squared. So we can put in our b value, which is e to the half, and also we've got ab squared, which is sitting up Well, you could just multiply the a by the b squared. B squared is going to be e to the 1, so if you square that, that'll be e to the 1. And e to the 1 times 1 and 2e is a half. Okay, so we've now found A and B, the contact point. So we've already worked out C, that's done. What's the equation of the common tangent? The tangent is y take y1, x take x1 equals slope. That's y1 and x1, that's the contact point. And the slope is 1 on B, because that's the derivative dy dx. If you come back here, dy dx, you can see here is 1 on B. We could have used 2ab, doesn't matter, they're both the same. We know B, so it's 1 on that value, and so multiply this whole thing over to the top, other side, and so there's our equation for the tangent. Last one is a motion question. So we've got the distance, velocity, acceleration. So derivative is the velocity, second derivative is acceleration. You need to get the initial conditions, so substitute time 0 into SVA. C, discuss it as t goes to infinity. As t tends to infinity, we look at the velocity. It's only asking for velocity. If t goes to infinity, this whole thing, e to the negative, that's e to a positive, that's e to a negative, that will head towards 0 as t goes to infinity. If that goes to 0, this goes to 0, so the whole thing goes towards 100. So this should have been 100 here, goes towards 100. Okay, next one, D, sketch the graph of the velocity function. So we know it goes towards 100, and also it starts at 60, initial condition, so we head it up like that towards 100, the asymptote. E, find the velocity of P when the velocity is 80 centimeters a second. So we put 80 for velocity and we solve for t. So you take 100 over that side, then you divide by minus 40, and then you take limbs at both sides. And so that'll give this value here. So that looks like roughly around about that value there. We'd have the coordinate, which will give 80, the answer we just found, minus 5 ln a half. That's this value here, minus 5 ln a half, 80. Okay.